is section 2.3. All right, so first thing that we need to talk about is what do we mean when we talk about a biconditional? What, not even thinking of math, what does the, when we use the prefix bi, what does that mean? What's that? The opposite? Two. Means two. So we're talking about, it has something to do with two conditionals. So a biconditional, we talked about a biplane, bi-level house. So we're talking about two. A conditional is a combination of a true conditional if we don't start with a true conditional, then it's not really something that we want to work with, and its true converse. So to make a biconditional, we want to start with a true conditional statement, like the one we used in our opener. If today is Thursday, then tomorrow is Friday. And its true converse. So that's our opener also had a true converse. So we're saying that both parts are true, and we write them by joining both parts with the phrase if and only if. And our symbol is we write P and then we have a two-sided arrow and Q. And we read P if and only if Q. And this, we make this by a combination P implies Q, or if P then Q, and Q implies P. So biconditional means that both of these conditional statements are true. If P then Q, and if Q then P. We can take both parts and turn them around and get something that makes sense. So if we took our opener, if today is Thursday, then tomorrow is Friday, we decided that the converse of that was true. If tomorrow is Friday, then today is Thursday. We could write for that one, as an example, tomorrow is Friday. If and only if today is Thursday. So that would be the biconditional for the opener that we worked on. We could also write it the other way around. We could say today is Thursday if and only if tomorrow is Friday. So that would be an example of a biconditional. Biconditionals are important because we use them to make definitions. That's why our biconditionals work. Folks, let's put the electronics away, please. So I want to do a little exercise on making a definition. So we're going to find the conditional statements and its converse, and we're going to come up with a definition. So that's what I want to do next. So here is my. Let me grab these. Pictures. Make them a little bigger. No, it gets a little blurry. This gets a little blurry when I blow them up. But I think we can handle it. All right. So this is card number 1, card number 2, and card number 3. So card number 1 says these things are floppers. And card number 2 says these things are not floppers. And card number 3 asks us about several different ones. So looking at these two cards, these are floppers, these are not floppers. Would A be a flopper? A couple people say no. Why would this one not be a flopper? What's wrong with this one? What do you think, Brian? It doesn't have a dot inside. The dot is outside and only has one of the little leg things. How about B? Would B be a flopper? One person says yes. Jason says no. Now Leigh changed his mind. Okay, Marie says no. So what's wrong with B that makes it not a flopper? Jason. It has 2 dots inside. All of these just have 1 dot inside. This one that has 2 dots says it's not a flopper. How about C? Would C be a flopper? Got a no right away there. Anybody else? What's wrong with C? It has 3 dots inside. Anything else wrong with it that would be a... What do you think, Marie? It doesn't have the leg thingies. So this one wouldn't be. How about D? This is D. So we got a couple of people nodding yes. A few more people nodding yes. So we think that one's a flopper. So we're going to say D is. How about E? Jordan says yes. Marie says no. What's wrong with E? Yeah, the dot. There's a dot right there. Is it hard to see it there? Yeah. Oh yeah, the color makes it hard to see. Yeah, let me make it bigger. So there was a dot there. Can you see it now? Yeah, the color doesn't really show up. Here, I'll do it in. It was supposed to be black, but it does have a dot there. So is E a flopper then? Now that it has that dot? Yes. So E is. So what makes a shape, what makes this thing a flopper? What's important to be a flopper? What do you think, Marie? Okay, it has to have 1 dot. How about this one? This one has a dot. On the inside. Okay, there we go. And 2 legs. Okay? So I'm going to say, let's write a conditional statement. If if it is a flopper, then has a dot inside. Let's call the dot, how about if we call the dot the I? Just so I don't have to write a dot inside. It has an I inside and two legs. And now let's make the converse of that statement, of that conditional. So we would say if it has what? How would we make the converse? I'll go one a little further. And we're making the converse of this statement. So what do we do for a converse? If it has two legs, so I'll do it that way. If it has two legs and an eye, then it is a flopper. So our conditional statement is true. Do we all agree? If it is a flopper, then it has an eye inside and two legs. And our converse, if it has two legs and an eye, then it is a flopper. That's kind of what this is all telling us. So now let's write a biconditional. We're going to make a definition of a flopper. So our definition is our biconditional. So how am I going to write my biconditional from these two conditional statements? Who can help me out? What do you think, Faith? Okay. And let's put the if and that would be okay. Usually you put the if and only if it kind of in the middle. So how would we put it in the middle? How about I'll start you out. It is a flopper. It is a flopper if and only if it has two legs and an eye. So that would be our definition of a flopper. We would make the biconditional statement. The conditional is true. The converse is true, so we combine it by putting an if and only if between the two parts. It is a flopper if and only if it has two legs and an eye. And I could write it the other way around also. I could say if it has two legs and an eye, would that work? If and only if. So yeah, I guess that wouldn't work as well that way. But normally you can do it in the other order also. We could say a shape with two legs and an eye. No, that wouldn't work either. Okay? So this is our definition. We take the conditional, we take the converse, we put the two parts together with if and only if. So we make it into a biconditional, and that becomes our definition. And we can also make a Venn diagram for our biconditional. So let's draw a Venn diagram for our definition. So our Venn diagram would look like this. And inside my flopper rectangle, I would have two legs and an eye. And I can also make one for the other part. So inside this one would be a flopper. And then this would be two legs plus an eye. So that would be our Venn diagram for our biconditional. If it is a flopper, then it has two legs and an eye. If it has two legs and an eye, then it is a flopper. So we all good on that? On our flopper example here? All right, so I want to practice a little more with biconditionals, making biconditionals, taking biconditionals apart. So I want to do a few more examples with these. All right, so our conditional statement is if two angles add to 90 degrees, then they are complementary. And if we were being more technical, we would say if the measures of two angles add to 90 degrees. So I'm leaving that part out, just so we can not write quite so much. So if two angles add to 90 degrees, then they are complementary. Is this conditional statement true? We say yes. This is what we said complementary means. So this is true. Let's write the converse. So how are we going to write the converse of this particular conditional statement? Can you help me out, Tristan? If I'm going to say two angles, and the are complementary. There we go. Are complementary. They add to 90 degrees. So that's our converse. We just switched the hypothesis and the conclusion. Is the converse true? If two angles are complementary, then they add to 90 degrees. Is that true also? Saying the same thing, really, right? So that is true. So we have a true conditional and its true converse. So let's write the biconditional. So the biconditional, we're just going to take both parts and combine them, but with if and only if. So how would we do that, Mitchell? Okay, so let's look at our original conditional. What's the hypothesis? What's the first part? So I'm going to say two angles add to 90 degrees, and then I'm going to put if and only if and only if they are complementary. So that would be our biconditional. We just take one part and put if and only if, and then put the other part. And I could also, this one, I could definitely write the other direction. I could say two angles are complementary if and only if they add to 90 degrees. So I could write it either way, and either way would be correct. And because the conditional, the converse, because both parts are true, this would make a good definition. Because both parts of the biconditional are true, this would make a good definition for complementary angles. Questions on that example? So let me write under here in red, I'm going to say good definition. This would be a good definition of complementary angles. All right, let's look at another one. We'll go the opposite way this time. So here is my my biconditional. Two numbers are, and we're going to use some fancy words here, but the fancy words really don't mean, are not important to what we're doing. Two numbers are additive inverses. If and only if they add to 0. So I'm going to say two numbers are additive inverses if and only if they add to 0. So we want to take this one apart. We want to write this as a conditional and a converse. So let's write a conditional. So we're taking this apart into two pieces. So for our conditional, I'm going to say if. And what do we want to write for the first part of our first conditional? Can you help me out, Maddie? So that would be the first part. You have two numbers. Are additive inverses. Then, what would be the next part? They add to 0. That would be our conditional. And now to do the other part, we're just going to form the converse of this. So what would be the converse of this? Can you help me out, Evan?
If numbers add to 0, they are
Yeah. So if two numbers add to 0, then they are additive inverses. So to take apart a biconditional, you just take the first part and turn that into, put an if in front of it, turn it into a conditional, and then make the converse, switch the order around. So that would be our conditional and our converse that comes out of a biconditional. Every biconditional can be broken up into two pieces. So we can go either way. We can turn a conditional and a converse into a biconditional. We can turn a biconditional into a conditional and its converse. So questions on that example? All right, so I said that we use biconditionals to make definitions. For something to be a good definition, we need we can write it as a biconditional, but we also want a few other things out of a definition. So we want to use terms that we know what they mean. So if we were talking in this class and I started talking about additive inverses, we might have an idea of what that means. But if I started going on and on about additive inverses, we might be confused because we don't necessarily know what that means. We want to make sure we're using words, we're using terms that we know what they mean when we write a definition. We want them to be precise. So for this example, I wouldn't say that we put them together to get 0. I want to make sure that we're saying we add. We don't want to say that they're sort of 0. We want to say they're exactly 0. So we want our definition to be precise. And the last thing, and this is what we've been talking about, is that they are reversible. And reversible means that we can write them as a biconditional. and we want our biconditional to be true. So you'll get homework problems and they'll say, is this definition reversible? So what that means is, can you read it as a biconditional and does it work both ways? So if we go back to our example that we did with complementary angles, we can say if two angles add to 90 degrees, they are complementary. That's true. And if we read it the other way, if two angles are complementary, then they add to 90 degrees. Both parts are true. So we would say that is reversible, because the biconditional works both ways. So this is how we make a good definition. We need a true biconditional. We've already talked about that. But we want to use terms that we know what they mean, and we want to be precise. So let's look at an example and decide if this is a good definition. Is everybody good with this idea of a definition? Okay. So here's an example. I'm gonna write a definition. An equilateral triangle has three congruent sides. And the question is this reversible? So first off, do we know what equilateral means? What does equilateral mean? They're all equal. Lateral just means sides, and equa means equal. So is this reversible? So what this is asking us is, can we write it as a biconditional? So it's saying, can we say an equilateral triangle has three congruent sides? And can we say a triangle with three congruent sides is equilateral? Can we say that both ways and have it be true? Equilateral means three the same sides. So the answer to this would be yes, because I can write a triangle is equilateral if and only if it has three, and I'm going to use a symbol for congruent sides. So a triangle is equilateral if and only if it has three congruent sides. So that would be a good definition. We can write it as a biconditional, and our biconditional works both ways. One downside of logic, lots of words. So you have to write a lot of words. All right, the last thing we need to talk about. How would you guess that we show that something is not a good definition? We need to find something to show us that a statement is not a good definition. What have we been finding to show that things are false? Bay says counterexample. By finding a counterexample. So this is how we show that a definition is not a good definition. We find a counterexample. How many do we need to find? One. We only need to find one. So if we can find a single counterexample, that shows that our definition is not a good definition. So next, I just want to find, just practice finding some counterexamples for some definitions that I write up. You can write them down if you want. You don't necessarily have to write them down. I want you to practice finding these counterexamples. So my first definition. Dogs are animals with 4 paws. So if I wrote this, the question is this reversible? If an animal is a dog, then it has 4 paws. If it has 4 paws, then it is a dog. Is that reversible? No. So this would be not reversible. So this would not be a good definition. So if I wrote that biconditional, if I said a dog is an animal if and only if, or an animal is a dog if and only if it has 4 paws, what would be my counterexample? A cat. A cat has 4 paws and it's not a dog. So this definition is not reversible. Squares have 4 sides. So we're saying, someone already found a counterexample. My biconditional would be a shape is a square if and only if it has 4 sides. Well, what's another shape with 4 sides? A rectangle. So this is not good definition. I'm going to say not. And our counterexample would be rectangle. Rectangles have 4 sides and they are not squares. And our counterexample here would be a cat. That's what we came up with. How about Tuesday? We should have this one down by now. Tuesday is the day before Wednesday. So if we wrote this as a biconditional, we would say it is Tuesday if and only if it is the day before Wednesday. Is that a good definition? Is it reversible? It is Wednesday if and only if the day before is Tuesday. So this is like what we did on our opener. So this would be, yes, good definition. And I could write this as a biconditional, just like we found that we did the converse of our opener, and we found that both parts were true. So we'd say, if it is Tuesday, then it is the day before Wednesday. If it is Wednesday, then the day before is Tuesday. And we could write it as it is Wednesday if and only if the day before is Tuesday. And what would be wrong with this one? An acute angle has a small measure. So what would be wrong with that as a definition? Well, first off, let's remember what an acute angle is. What is an acute angle? Less than 90 degrees. So is this a good way to describe an acute angle? No? What's wrong? Small. Right. What does a small measure mean? Do they mean 10 degrees? Do they mean 20 degrees? Because how big an angle could be acute? 89, how about 89.999 degrees? Is that small? No. We don't know what they mean by small. So this would be this is not precise, is the problem with this. And our counterexample to this would be 89.99 degrees. I would say that's not really small. So this is my counterexample, and this is also not precise. If we said an acute angle has measure less than 90 degrees, then we'd be doing a little better. So we need to be precise also. And this would be our counterexample, 89.99. I would say that's not really small. All right, questions on biconditionals. If and only if. Works both ways. We use them to make good definitions. All right.